So this is the first attempt at recording the homework key. Hopefully this will help a little bit, but anyway, let's get going. So when a rigid object rotates about a fixed axis, what is true about all the points in the object? There are more than one correct answer for this question. A, they all have the same angular speed. B, they all have the same tangential speed. C, they all have the same angular acceleration. And D, they all have the same tangential acceleration. And E, they all have the same radial acceleration. If we look through these options, tangential speed, tangential acceleration, and radial acceleration are all going to have to depend on the radius of the particular object. So the further that it is from the center, the higher that tangential speed or tangential acceleration would have to be. However, each of the angular measurements, so the angular speed and the angular acceleration, each of those are going to be the same for a rigid object turning at a constant rate. So A and C are going to be the same for us. So those are the two correct answers for this first question. Question 2 is a lot like the example we saw in class where we saw the eagle was looking for the smallest object that it could see. In this case, they give us the diameter of the moon, 3.47 times 10 to the 6 meters, and the angle it subtends when viewed from the surface of the Earth. So if we're thinking of this as a diagram, here we've got our Earth over here. Somebody's standing on the Earth and looking towards the moon, so the moon would be somewhere maybe over here. So the angle, obviously that's a little bit larger than the moon, but the angle to that they give us. So they give us that theta in terms of radians, which is always good. We always want that measurement in terms of radians. And then they give us the diameter of the moon. But in this case, if we notice the diameter of the moon, again, because it's such a small angle, because it's only 0.00904 radians, the diameter of the moon is going to be very, very close to the arc length as well. So the arc length and the diameter are not going to be off by very much. Because of that, that allows us to take advantage of the relationship between our linear measurement for x, the arc length, and our angular measurement for theta. And if you go back to your notes, that's the relationship that x equals r times theta. Well, if we take for granted that the moon's diameter is basically the same as x, then we now know our measurement for x. And then we're looking for the radius because we're looking for the distance from the Earth to the moon, so we're looking for our r. And they give us the theta as well, and theta's in radians, which we already want. So this problem then just becomes a simple calculation problem. 3.47 times 10 to the 6th equals the radius times my angular measurement. And then we just have to calculate this. So when we divide both sides by the angle there, we get our final answer, and we find our radius to be about 3.84 times 10 to the 8th. And the units for that are going to be in meters for us, and that's going to represent the distance between the Earth and the moon. Question 3 is a relatively simple question, just asking us basically to convert the angular speed from revolutions per minute to radians per second. So again, we saw this a few times in class. I know most of us are probably already comfortable with it, but obviously I'll show you how to do it as well in case you should need it. So 813 revolutions per minute. We want to convert that to radians per second. Well, one revolution is 2 pi radians, and 1 minute is 60 seconds. So then once again, just calculating 813 times 2 pi divided by our 60 seconds. And we should get that to be about 85.1. So it's about 85.1 radians per second. This question is maybe one of the trickiest ones on our first homework assignment here, so it seems simple enough in the context. Two people start at the same place, walk around a circular lake in opposite directions. One has an angular speed, so they give us the angular speed for each individual. One has a speed of 1.7 times 10 to the negative third, the other has 3.4 times 10 to the negative third. How long will it take before they meet again? Okay, so the approach to this problem, there's a couple different ways you can go about it. No matter how you do it, you've got to be pretty comfortable realizing that if you've got a circular lake, so we've got something that's roughly a circle, two people are starting at the same point, They're walking opposite directions. By the time that they meet, we have to think about what's the total angle that they'll have covered. So what's the total angular displacement? Well, we know that by the time they meet up, they'll have to have made a full circle. So their total angular displacement will have to be 2 pi radians. Well, what that tells us is theta 1, the angular displacement of the first person, plus theta 2, the angular displacement of the second person, has to equal a total of 2 pi. At this point is where you have kind of two options in how you can work this problem. You can either try to set up a system of equations. Since we know that angular velocity, since we know that w is defined as change in angle over time, we could set that up for each individual. So for instance, the angular velocity of the first person, which we know is 1.7, would equal their displacement over the time. Then the angular velocity of the second person. The key here is relating the angular velocity of the second person, the angular displacement of the second person, to the angular displacement of person 1. And the way that we could do that is, if we know the first person went theta, or theta subscript 1, we know the other person would have to go the remaining 2 pi minus that theta. So that way we have, if we set it up this way, we've got two equations with the same two variables. T is the same amount of time for each person, and theta 1 would represent that same angle measure regardless of the person. So you definitely could do it this way, solve the system equations. A slightly easier way to do this would be to set them up again separately. Okay, so angular velocity equals the first person's displacement over time, and then if we solve for their displacement, we would see that theta 1 equals w1 times t. If we do the same thing for the second person, theta 2 equals, w2 equals theta 2 over t, and then solve for that theta 2 equals w2 times t. Again, the important conclusion here is the time that it takes each person is the same. If we then bring these two thetas together in our original relationship, knowing that they have to equal 2 pi, it's a little bit easier equation to solve. We can just plug it in and then solve from there. So we take this quantity, plug it in up here. We take this quantity, plug it in over here as well. And again, we take advantage of the fact that we do know that they are the same time. So we take our angular displacement times time plus our second angular velocity times time equals 2 pi, and we plug in the numbers that we know. So 1.7 times 10 to the negative third t plus 3.4 times 10 to the negative third t equals 2 pi. And then it's just a matter of solving for t. So combine your like terms, 5.1 times 10 to the negative third t equals 2 pi, and then solving for t we get about 1,232 seconds, which may seem like a relatively long time, but if you also look at their angular speeds, they're not moving real quick with it being 10 to the negative third. So 1232 is what that's supposed to say. It's not a terribly large number compared with those angular velocity. The next question, question 5, is a pretty straightforward example of just angular kinematics. So if we look through this, when a fan is turned off, its angular speed decreases from 10 radians per second to 6.3 radians per second. So there's my initial angular velocity. There's my final angular velocity. And then they tell us it takes 5 seconds to do that. Okay, so we know 3 of our 4 measurements for kinematics. What is the magnitude of the average angular acceleration, which is my alpha that I'm looking for? Okay, so all this one really is in a pretty straightforward application of angular kinematics and solving from there. So looking at these variables, we would use our WOTAT formula, if you prefer to think of it that way. So our final angular velocity equals our initial plus our acceleration times time. We know that our final velocity is 6.3 equals my initial 10 radians per second plus alpha is my unknown times 5 seconds. So again, just a matter of solving this and going from there. We would get negative 3.7 equals alpha times 5. And at this point, I know you guys all love your 5 rule. It's just dividing by 5, so No big deal, we can all do this, right? Double that number and move the decimal point 1 over. So we get negative 0.74 radians per second squared. And do make sure it makes sense. So the fact that it's negative, because it's slowing down, and we defined our initial velocity as a positive 10, because it's slowing down, the acceleration definitely needs to be a negative number, so that all checks out pretty well. So not too bad. This next one's very similar to the last in the sense that it is going to be a angular kinematics problem, but it does have a trick involved, and that trick comes kind of in that first sentence here. So the string of a toy top is 64 centimeters long and is wound around the top at a spot where the radius is 2 centimeters. Thickness of the string is negligible, the top is initially at rest, someone pulls a free end of the string, and a winding top giving an angular acceleration. So looking through there, we do know that the initial angular velocity is 0. We know our acceleration is 12 radians per second squared. And then we're looking for the final angular velocity. So we know we're looking for our final omega there. So the trick becomes, again, looking at that first sentence. So they give us the total length of the string. Well, if we can kind of picture the top from looking at it from above. So here's my top. It's got a radius of about 2 centimeters, so they give us that radius there. We know 2 centimeters. If the total string is 64 centimeters long, that string is going to wrap around and around and around this top, right? And it's going to do so more than once because that 64 centimeters is going to be more than the circumference of the circle. The trick is, how can we use that 64 centimeters to help us? And obviously the key is we need to be looking for one of our other two measurements. Can we find either theta or can we find time? Well, we don't necessarily know anything about the time because they give us this measurement of linear distance. But instead, since they're giving us the distance of the string, they're giving us really the total arc length that string goes around the circle. Okay, so the total arc length, x, is going to be that 64 centimeters that we're going with. So then the question becomes, how can we relate x to an angular measurement, in this case theta? Well, the relationship there, again, if we go back, is x equals r times theta. So the fact that they tell us the total length of the string allows us to know the total amount of arc length we cover. We can relate that through the radius to theta. Now, I have kind of shortchanged this a little bit here. I know that both of the units are actually in centimeters. However, as long as both sides are in centimeters, I should still get the same proportion for my theta. Okay, so if you wanted to leave it in centimeters, you could. If you wanted to write it as 0.64 equals 0.02, should give us the exact same thing. And when we solve for theta, we get 32. Okay, so this 32, the good news about it is because I'm using this equation, that is coming out in radians, which is exactly what I need to use my angular kinematics for the question above. Okay, so now I've got my angles. It's going through a 32 radian angle. I've got my initial velocity, I've got my acceleration, so then I just need to find my final. Okay, so using kinematics, you can do any number of them, but to do it directly I would choose this formula and then solve for my final angular velocity. So solving then for my final angular velocity, I just plug everything else in. I know that 0 plus 2 times 12 times 32, and obviously just watch your calculations to make sure you do end up getting about 27.7 radians per second. So again, the trick of this problem, and oftentimes the toughest problems in general, are going to be those where we have to take these linear relationships, and it's not always exactly clear what it stands for, but try and think it through and identify what does that 64 actually represent. Once you realize it represents the arc length, which is Rx, it's a pretty easy transition to finding our theta. But until you get there, this problem can be pretty tricky.